All right, so let's get started with today's lecture. Okay. So, as before, okay, now I'm going to spend more time on the limiting, or maybe we should refer as before as the long run analysis of a continuous time Markov chain. Okay. So as before, well, okay, I'm going to denote by X. Okay. A continuous time Markov chain. Okay, on some state space E, which consists of integers. Okay, or which is just a subset of integers. And to characterize this process, right, it is enough to specify the rates of these holding times as well as the one-step transition probabilities at the end of each holding time, right? So for each state, okay, for each state I, suppose that the rate of holding time in state I and the one-step transition probabilities for going from state I to this state J different than I are also given. Okay, so this is one-step transition probability, okay, for going from state I to another state J different than I. Right? When they are given to us, we know how to simulate a Markov chain, right? Continuous time Markov chain. We just drew this picture before, right? For some time we stay, for an exponentially distributed amount of time, we stay in the initial state I, let's say, and at the end of this time, it just the Markov chain jumps to a different state, state J, according to these probabilities. Right? It jumps to another state, let's say J. And this happens with probability Pij. The Markov chain could have actually jumped to another state K, perhaps, right? And that would have happened with probability Pik, right? If it is here, it stays there for a while, for a time which is exponentially distributed. This time with rate determined by this state J, right? So this is an exponentially distributed random variable with rate Vj, right? And this was an exponentially distributed random variable with rate Vi. And this process goes like this. If the next state into which the chain continuous time Markov chain jumps is K, which then happens with probability Pjk, right? It stays there, and so on and so forth. Okay? So that's a typical sample path of process xt as time t progresses. Okay, and then we define this so-called Q matrix, right, which consists of infinitesimal transition rates. That's sometimes what people call transition rates. Okay? And Qij, right, is minus the rate of the holding time in state I. Sometimes I use this, sometimes the other. Perhaps we should also write this like we saw by, in order to remain consistent with all these, right? So this is Vi when J equals I, and when J is different than I, this is Vi times probability of moving from I to state J. Okay? When we have this matrix Q, last time, right, we wrote a differential equation that the one-step transition probability function is supposed to satisfy. So we denoted first of all by this the conditional probability that at time t continuous time Markov chain is going to be in state J, given that at time 0 it was in state I. Right? And then we show then first derivative of this function with respect to t is what? Q. Okay. The Q ik times pkj t, where the sum is over all states k in the state space. Right? So this is true for every ing in the state space and t, but we wrote this one compactly in terms of matrices built by using these ij entries, right? So because this is itself like a matrix multiplication, right? So this is, you take the ith row, you take the inner product with the jth column of transition function at time t, and this can then therefore be written like this. Okay? And we show that the solution for this equation, together with, so this is not enough to specify a solution uniquely, right? At time 0, when t equals 0, going from I to j, right? When t equals 0, if you are in state I at time 0, then you will be in state j at the same time 0 with probability 1 if j equals I, with probability 0 otherwise. So therefore, Pij at time 0 is going to be either 1, right, or 0. 1 if j is the same as I, 0 if j is different than I. And in the matrix form, this is nothing but just identity matrix. Right? You have ones only along the diagonal. Right? So then this is an initial value problem. So you know the initial at time 0 what the value of this unknown function is, and you know that it satisfies this differential equation. And we show that the solution for this one is given by, okay, that's the notation. By this what we mean is, or this is defined as t to the power n divided by n factorial times the nth power of Q matrix, right? This matrix. Okay? And here you take the summation from 0 to infinity. So you have a matrix on the left-hand side, therefore you have a matrix on the right-hand side. They match each other. Right? It makes, this equation makes sense. So the ij entry of this is going to be like what? You calculate, you find the ij entries of all these powers of Q matrix, you multiply with these numbers, and then you sum them up. Right? That's how we get that. And this, and then starting from this, we also showed that, or we argued at least that we would expect P also to satisfy this equation. Okay? So instead of multiplying from left, you may multiply P from right, and you may still get the first derivative of transition function at time t. Okay? This is always true if the state space E is finite. And in other cases, you have to be careful. It may or may not be correct. And in applications that we are going to see, this is satisfied. This equation is going to be satisfied. As I said, if it's finite, we don't have anything to worry about. And then they have names. This one is called as Kolmogorov's backward equation, right? Kolmogorov's backward equation. And this is called Kolmogorov's forward equation. Okay. All right. And now, when we start discussing the limiting probabilities, okay, limiting properties of this Markov chain, this equation is going to be useful. Okay, and in general, okay, under certain conditions which are going to be satisfied in many of the examples we are going to see. Okay, the limit as t goes to infinity, okay, Pijt will exist, okay, and is the limit, the value of this limit, okay, and its value is gonna be independent of the initial condition, independent of the initial state, right? It is I in this case, and we will give a name to this one. As before, perhaps I will just denote it by pi j. Okay? So we remember that this is, right, is the probability that starting in state I at time t the chain is going to be in state j. Okay? I'll again list actually the sufficient conditions for this limit to exist, but then we have to worry we'll pay more attention on how we can find these values, okay, and what their interpretation is, and how we can use them to analyze the long-run behavior of this Markov chain. Okay? And for the time being, let us assume that these limits exist. Okay? For every j in the state space, for every I as well, okay, and let us assume that it is independent, right? It doesn't depend on the initial state I. Okay, then we can use, as I said, the Kolmogorov's probability equation to find a list or a system of equations that these probabilities pi's satisfy. Okay, and what are they? So let's take this one. See, I can just take the limit of both sides, right? Now the limit of each entry of this matrix, which are these, right, will exist. Now this is a limit, okay? And then that just, since the right hand side has limit, then left hand side must have a limit. And we will argue that the limit of left hand side has to be 0. Right? Nothing, no other value but 0. And then immediately we are going to get a system of equations that these limiting properties pi must satisfy. Okay, and we may perhaps look at this Entrywise expression or form of that equation, right? So the Kolmogorov's forward equation, which in matrix form we wrote as the first derivative of matrix P equals matrix P, right, the transition function at time t times Q, and now this is for every I at j, this equals therefore the sum of Pi k at time t times Q k j, right, where we take the sum, and now assuming that the limits of these, or limits of transition function for every I and k exist, we can take the limit of both sides. Since the limit of right hand side exists, the limit of left hand side must also exist. Okay. And I assume that we can interchange the order of this, the limit and the sum. We can always interchange the order of the limit and sum if the state space is finite. Otherwise, we have to be careful. But let's assume what we can do at best if everything goes right. Okay, we interchange the limit and the summation. The limit of this thing is what? Limit of this times this constant, which doesn't depend on t. Now, we assumed, right, this not only exists, but also depend only on the state into which the chain is going to move, right? It is independent of I, the initial state. And therefore we get what? We get pi k times q kj. Okay, like this. Now, what can we say about the value of this limit? Okay? What is the limit as t goes to infinity, the first derivative with respect to t of transition function? Okay? For example, can it be positive? Right? Could we have this to be true? Huh? What happens if this is positive? If this is positive, okay, then that means by the definition, right, for large t's, all these numbers are going to be away from 0, right? Because this number, right, it is like if you look at the t, if it is positive, maybe it will just fluctuate, but then will converge to some positive value, right? And it is going to stay in the neighborhood of that number, right? That basically says that there is, there is some positive epsilon, no matter how small, and some large, let's say, fixed number t, such that for every t greater than this, if t is large enough, okay, then the value of this function is going to be away from 0. So it is going to be bigger than epsilon. Right? And if the derivative always stays away from 0, what does that mean? If you just integrate this thing, right? So if you look at the Pij t minus Pij capital T, which is the integral from t to t of this, its derivative, but it is greater than epsilon, if this is true after t, for each t after capital T. So this is going to be then greater than epsilon times t minus t. Right? And this is true for arbitrarily for every t at least larger than capital T. Right? And then what does this mean? To find the value of probability, transition probability, probability of going from I to j in t units is this constant plus, or it is greater than, right, because of this, t minus t. Right? We have this. So this is true for every t greater than t. But does this make sense? Does this make sense? What does this imply? No matter how small epsilon is, since it is still strictly positive, right, you can always choose t large enough that this thing is going to be itself greater than 1. You can make that greater than 1. Right? Right? If t minus t is greater than 1 or epsilon, or if you choose t, right, t plus this, then the product is going to be greater than 1. But then that suggests that, right, that suggests that Pij, the transition probability, is going to be bigger than 1 for every large t. Which doesn't make sense, because this is supposed to be a probability. It cannot be bigger than 1. So why did I get this nonsense? Well, I asked myself, what happens if the limit, which we know now exists, is greater than 0, right? So this cannot be the case. So this cannot happen. Right? Then the next question that you are going to ask, well, can it be negative? Right? Could we have the limit which we know exists, right, is strictly negative? Well, you can actually play the same game. In that case, okay, there will be an epsilon again positive and a t, large t, perhaps, right? Such that if t is greater than t, or for every large t, in this case that means greater than capital T, right? This tells us that this is going to be away or below minus epsilon, okay? Namely negative. But then you look at the same identity over there, right? So this difference, as before, can be calculated as the integral from t to t, the derivative of the same transition function, which we know that now is less than, the integral is less than minus epsilon for each s after t, and therefore this is going to be bounded from above by minus epsilon times t minus t, or Pijt, right? Transition probability in t units from I to j is less than Pij capital T minus epsilon times t minus t, right? But then, if t is bigger than, right? So this is going to be positive. It doesn't really matter, though. Right? If t is large enough, then we can always make this thing an enormously small negative number. Right? We can make this arbitrarily negative, right? And so negative that it is going to just wipe out this positive quantity, and the entire thing is going to be negative, right? But that is then, right? We can just write that for large t, right? Pijt becomes negative, right? Which contradicts, right? Which contradicts with the fact that Pij is in fact a probability, right? So this cannot be true either, right? This is also not true, cannot be true, right? And what is the only possibility left? As t goes to infinity, the derivative of this transition function must be 0. Okay, we must have that. Okay? What use does that have then? So we go back to this one, right? We have this relation, and in this relation now we know the left-hand side equals 0. Okay, and now we can conclude that, right? Okay. If you take the limiting probabilities pi case, right, and calculate this sum, you must get what? 0. And this should be true for every state j in your state space. Okay. Right. So if we treat pi, right, consisting of all pi k's as a row vector, right? And we know that this is the kj entry of Q matrix. This is nothing but what? Row vector pi multiplied from left with, or row vector pi is multiplied from right by matrix Q, right? And we have this. Okay? Now we have an equation that pi must satisfy. Since pi is supposed to be a probability distribution, we also have to make sure that if we ever attempt to solve this system of equation to find pi, the solution is the one. If there are more than one, we pick the solution which gives this identity. Okay, I never use the states in this discussion. So any solution of this system which also satisfies this, right, is going to be a candidate for being the limiting probabilities of the underlying Markov continuous time Markov chain. Okay, and sufficient conditions for a continuous time Markov chain to have unique limiting probabilities well, I should say limiting probabilities always are going to be unique by definition, but I guess what I was trying to refer is that it is also going to be unique solution of this system of equations, but I am going to come back to that. Sufficient conditions for Markov continuous time Markov chain to have limiting probabilities are, okay, for example, first of all, well, it has continuous this chain, right? Continuous time Markov chain has finite state space. Okay, maybe I should write I, the first one, and the second condition that the states communicate with each other. Okay, namely, for any two states I and j, okay, there exists some t such that in t units of time, or after t units of time, probability that I will find the chain in state j starting in state I is going to be positive. Okay. Now, not all the continuous time Markov chains we will be working will have finite state space, but then we have a backup that we can check against, and that says that that the states, okay, of Markov chain are positive recurrent. A term that we did not discuss in our discussion of Markov chains, but this basically means that each state is going to be visited infinitely often. If we have finite number of states, then, and if they are all communicate with each other, then this is always going to be the case. Okay, so having just finite state space along with the second statement would imply that the chain is going to be positive recurrent all the time. Okay, but if chain does not have finite number of states, it may actually just go and get absorbed in the infinite along an infinite sequence of states without ever coming back. So that can happen. So against that, this is the protective or the sufficient condition that we would want to check. And that basically says that the chain comes back and visits each state infinitely many times or infinitely often, and the time it takes to come back to the same state on average is going to be finite. So it is not going to visit the states infinitely often, but it is going to visit the states on average after finite amount of time. Okay? And that intuitively makes sense, right? For the limiting probabilities to exist, what does this mean? Limiting probability is going to be positive, and it will obviously mean that the number, whatever it is a fraction of time the chain spends there, if it is positive. Or for that to be positive, you should you better actually visit each state, right, infinitely often, because after finite number of states, if you leave the state without ever coming back, then the fraction of time, right, you are going to, or the chain is going to spend in that state is going to be basically zero, because you are just living without ever coming back, right? So therefore, recurrence, right, it just means what it really means, right? So recurrent, it will repeat itself. You will repeatedly visit that state. Positive is actually the word positive or adjective positive here points that actually we are looking for in a strong recurrence, in the sense that, okay, on average, even though you may come with probability 1 back to a state, the time on average it takes to come back to that state may still be infinite. So having a random variable which is finite with probability 1 is something. Having a random variable with a finite expectation is something else. There are random variables which are finite almost surely or with probability 1, but still having infinite expectation. Right? We don't want such things. If it comes to, if the random variable we are talking as here is the time it takes for the chain to come back, recurrence means that it should be finite almost surely or finite with probability 1, but also its expected value should also be finite. So it should really, you want the Markov chain really come back and visit infinitely often, on average in finite time, each state. Okay? As I said, if you have Markov finite state space and you know that chains states communicate with each other, so there are no absorbing subset of state space into which whenever the Markov chain gets, it cannot get out. If you don't have such things, so if you assume just the states communicate, you actually eliminate that case, then each one of these finite states is going to be actually visited infinitely often, and the time it takes to come back to each one of these states is going to be on average finite, and then we will be fine. So these two things will just imply that a finite state space continuous time Markov chain is always going to be positive recurrent. But if it doesn't have finite number of states, then we just have to just state this, right? Okay, we have to check or to make sure that this holds if you want to make sure that limiting probabilities exist. Okay, and the other thing is how we interpret the limiting probabilities. Limiting probabilities, when they exist, okay, so that's one important remark. The other one is, okay, limiting probability let's say pi j for a fixed state j also gives us long run average time, okay, long run average time spent by the continuous time Markov chain in state j. And the connection, the proof of the connection is exactly the same as what we have done for the discrete time Markov chains. But first, well, the time, right? If you want to calculate, let's say, the total time spent by the continuous time Markov chain, right, in state j until time t, then what are you going to do? Well, at each time little t, okay, you will check if the Markov chain has been in state j or not, and then you just sum them up, right? As in the Markov chain, discrete time Markov chain case. This especially makes sense if just you look at the picture, right? So we said a typical sample path of a continuous time Markov chain looks like this, right? So it enters into state, and we know that it is going to stay there for a positive amount of time, and then it is going to jump to another one. So it is actually, the sample path looks like what? Piecewise constant function. And this then gives what? So you take this from 0 to t, right? Let's say this is state j. So at each, so what we would like to calculate is the area under this function, right? Which is what? If you just look at this function for this sample, right? So this is xt, right? It was in state J only in this part, so you will have 1 in this case. The value is going to be 1, was indicator, the value of indicator function is going to be 1 here, and 0 everywhere else, right? So this is the function of t which has the value 1 whenever at time t Markov chain is in state J, and 0 everywhere else, right? If it entered J sometime later, let's say like this, then you would also have a piece of 1, a constant 1 like this. Perhaps it would just go like this before it jumps out of the state. But we are now interested in only the area under the curve, under this curve, right? So we have 0 areas here, and then whatever they sum up to will give us the time. Okay, so the time spent by x in state J over time interval from 0 to capital T. If you divide this by 1 over t, then you get what? You get the fraction of time the Markov chain, continuous time Markov chain, spent in state J over the interval from 0 to t. Right? So this is then average, or maybe I should say fraction. Right? And then we can take expected value of this, and then this is going to give you expected fraction of time, right? Proportion of time spent by chain in state J in this interval. T doesn't have any particular meaning for us, and since we don't know which T is the best to choose, perhaps we should just T as large as possible. So we take the limit again. And then this entire quantity will give us what? Long run, right? Long run expected fraction time spent by x, Markov chain x in state J. Okay? Then of course this part will not make any more sense, because the result will be independent of t, which is now a dummy variable for us. And you can again replace, right? So this is like a summation for us. We said many times that we can just interchange the order of summation and expectation. And if we do that, now we are going to have 1 over t, the integral from 0 to t, the expected value of this, the indicator random variable, and that is nothing but the probability that xt is in state J, right? And we may have been actually provided more information. For example, we may have been told that initially the chain starts in state I, and that can also happen, right? So then this is long run expected fraction time spent by x in state J starting initially, right, or starting at time 0 in state I, which we know that will not play any role if the limiting probabilities exists and does not depend on I, which is always the case if you have irreducible chain, namely all states communicate with each other. Okay, but anyway, so it doesn't harm to just look at this more general case. Then we will also use conditional probabilities rather than unconditional ones. Right? But this is nothing but transition function pt, right, for the pair ij, the probability of going from I to j in t units of time. Okay, we can show just the way we did in the discrete time Markov chains. This is going to have the same limit as the limit of the function we are integrating. Okay, because if the limit of these quantities exist, right, it is going to just converge and stabilize around a constant number in which, in this case, it is going to be pi j, and then you are, as if you are integrating a constant over this interval, and then you divide by t. Constant integral of the constant is going to be that constant times t, you divide by t, so you get the constant itself. So whatever the limit of this function is, as t goes to infinity, right? For large t, at least in the tail of this integration, this quantity will be approximated by the same limit, and the initial part is going to get killed again by this increasing the growing capital T, by which you divide everything. And for that reason, you will get actually, you can show, you can convince yourselves that this limit is the same as this one, and this is nothing but the limiting probability, right, of state J, or being limiting probability of being in state J, right? And then, okay, we got the same relationship. So whenever we would like to calculate the fraction of time the Markov chain spends on average, right, or the, in any given state J, then that is given by the limiting probabilities again, right? Okay. And so whenever you want to calculate any one of these quantities, now we know that we can just start by first solving these equations, okay, and then use them to answer the question. So there are other equivalent forms of these equations which may also be useful, just the way we actually derive in discrete-time Markov chains, right? So you remember we also talked about the equilibrium characterization of these limiting probabilities. We said that actually this system of equations can also be seen as, well, the mass being transported from one part of the state space to its complement, right, has to be exactly matched with the mass transported from its complement into itself, right? And that those type of conditions also give us some other or a rewritten version of these equations, but just paying attention to them sometimes also was helpful in solving certain problems. So we have a similar characterization of limiting probabilities for continuous time Markov chains as well. Let's look at them quickly as well before we see some examples. Okay. What are they? The first thing we should pay attention is look at this Q matrix first. Look at this Q matrix. If you just fix I and sum over all J's, what do you get? Huh? Is it going to be 1? If you sum over all J's different than I, then you are summing all these things over J's, right? Then this will become 1. This will go out of the summation because it doesn't depend on J, right? So you get Vi from. If you on top of that add this one as well, you get what? 0. So in this case, this is not like a positive transition probability itself. The sum of the rows of this Q matrix is always 0. Okay? So that's going to be useful, right? If you just sum Qij's or J wandering in state space, look at Qii and the sum of the rest separately, okay, Ij, J being different than I, then we know that this is minus Vi, and here we have Vi times Pij. Right? This doesn't depend on J, so we can take that out. The sum is going to give us 1 here, and then therefore you have Vi. So minus Vi plus Vi equals 0. Okay? And this is true for every row of Q matrix, namely for every initial state I. Okay? And we'll use this simple observation to show that, okay, pi solves the system of equations 0 equals pi times Q. Maybe we should just write this equations in the usual form, not in terms of matrices. So this is the sum pi I times Qij, right, for every I in the state space, if and only if, okay, pi I times, okay, Qij, I being in, let's say, set A, and J being in the complement of set A, the same as the sum of the same product of the same quantities. Now, J being in a, well, J, let me see, I being in the complement of A and J being in A. Okay? And the picture-wise, right, so we have the state space, and there is a set A, right? We have transitions going out of A, and there are also transitions coming into A, right? For each state I inside and J outside, for each pair of states I inside and J outside of set A, you have what? So you have pi I fraction of mass over there with this rate this time. It is not proportion but just rate. You transport all these things to state J and you sum this to find the total rate at which the material is being transported out of state A. You sum all these things for every I inside and J outside. Okay? So that gives us the total rate at which, right, if you wish, material, right, or maybe I should say mass, is transported out of set A, okay, and this is just the other way around. So for each I outside, see, and for each J inside, so this gives us, right, it is the sum of the rate at which material is being transported, or the same mass transported inside A, right? So then this is the total rate at which mass is being transported into A. Okay? And if pi is a solution for this system of equation, then it must also be a solution of this system of equation. In a sense, the limiting probabilities can also be interpreted as the equilibrium probabilities. Okay? Of course, this should be true for every choice of subset A. Okay? For every subset A of state space A. Okay? So why is this true? So we'll just discuss that after giving a 10-minute break, perhaps. Okay? Do we have any questions by now? Okay. All right, let us look at this after we are back from the break.